And so let me remind you that now we are moving to the second part of the session, which is from the high performance architectures and compilers topic. Therefore, please be advised to use a different Slack channel for this particular topic. This is TO4. Okay, so let us proceed with the. Okay, please remember that you can always ask your questions directly using Slack directly to the authors. So thank you again for providing this presentation. And now let us move to the final presentation of this session. Its title is OMP mem opt, optimized memory movement for heterogeneous computing.
Today I'm going to introduce our Europar paper OMP mem opt, optimized memory movement for heterogeneous computing. This work has been done in collaboration with Jisheng Zhao and Professor Vivek Sarkar from Georgia Tech. Host-to-device memory management is one of the most fundamental operations when offloading any computation to an accelerator like a GPU. It is a significant source of overhead both in terms of execution time and power efficiency. The reason for this host-to-device memory copy is that devices like GPUs have a separate device memory, and any computation that is launched on the GPU requires data. That data needs to be copied from the host to the device memory, and after the computation is done, the data needs to be copied back to the host memory. This host-to-device memory copy is usually very expensive and the performance bottleneck in many applications. So we did an experiment to quantify the significance of the memory copy time versus the compute time for 10 OpenMP 4.5 GPU target offloading benchmarks. And as we can see here, in many of these applications, more than 75% of the time is spent in memory copy. So let's look at an OpenMP target offloading example and understand how the memory management works. In this example, the user specifies the OMP target map directive, which launches this block of code on the GPU, and the clause map A means that the kernel will read and update the array A. And then on line 7, the host reads the value of the array A, and then again on line 8, the kernel is launched on the GPU, and the map A clause means that the GPU can read and update the array A. And finally on line 13, we again read the value of the array A from the host. So because of the map A clause, when copies the memory to the device and back from the device to the host, on line 6 we have a memory copy from device to host of the array A. And then on line 7, the host reads the array A. And then again on line 9, we have a host to device memory copy because of the directive on line 8. So here we are trying to show that the memory copy from the host to the device is redundant because the host didn't update the value of the array A, and the device already had the most recent version of the array A. An expert programmer can use OpenMP directives to optimize the data movement and remove any redundant memory copies. For example, the directive on line 2 ensures that there is a memory copy from the host to the device on line 3 and back from the device to the host on line 16. And then any other map directives inside this region would essentially be ignored. So there is no memory copy because of the directive on line 4. But since the host reads the array A on line 10 and the kernel had updated the array A on the device, we need to force a copy from the device to the host, and that's why we can use the target update clause here, which copies the array from the device to the host. And again, the line 11 target map directive doesn't cause any data movement from the device to the host or host to the device. In this case, we saw that the programmer can use some combinations of the OpenMP target directives to optimize the data movement, but this explicit memory management is non-trivial, it is time-consuming, and it could be error-prone. So now the question is, can the compiler help in this case? So to build any compiler analysis to detect redundant memory copies, first we need to define what is a redundant memory copy. In this example, we are showing three sequences of operations. First, the device copies the array from the device to the host, and then the host doesn't update the array at all, and then there is a copy back from the host to the device. So in this case, the host to device is redundant because the device already had the most recent version of the array. In the second example, there are again three sequences of operations. We copy the array A from the host to the device, we launch the kernel on the device asynchronously, and then we copy back the array A from the device to the host. In this case, we are saying that the array A was neither updated on the host nor on the device. Hence, both the host and the device have the same version of the array, so the device to host memory copy was redundant. And then there is a third very important reason for redundant memory copies, that is the loop invariant memory copies. In this example, the host is launching a kernel inside a outer loop iteration. So in every iteration of this loop, this kernel will be launched on the device, and we will copy the data from the host to the device and back from device to host in every iteration. So in this case, the host to device memory copy is only required on the first iteration. In subsequent iterations, the host to device memory copy is redundant because the host didn't update the array A. And similarly, the device to host copy is redundant in every iteration other than the last iteration because the host doesn't read the value of A inside the outer host loop. So we saw three common patterns of redundant memory copies, and the pattern here is that there is a memory copy from one memory space to another, and then neither of the memory spaces update the array, and then finally there is again a copy back from one of the memory space to another. So this pattern of redundant memory copies has a similarity with scalar redundancy also. So in the first case, this is our common sub-expression elimination, where the expression a plus b is computed on all the paths reaching this expression. Similarly, we have seen partial redundant expressions where this computation a plus b is evaluated on only one of the paths reaching. So partial redundancy elimination can be used for removing loop invariant scalar expressions. So we developed an intermediate representation to detect redundancies in the memory copies. Our intermediate representation is called location aware heap SSA, and in this we represent the array reads and writes and memory copies. In this example, we are showing a sample LASSA for this sequence of instructions. So let's look at our LASSA operators. The first one is an array definition operator denoted by D phi. The second is a array use operator denoted by U phi, and the third is a array copy operator denoted by MCPY. Now let's look at how we can perform our availability analysis on the on our IR to figure out which computations are redundant. So here, after the memory copy of the array from the device to the host, we say that the array is available on host and device because both the host and device have the same version of the array A. And then after any use of the array on the host or on the device, the array is still available on both the host and device because both of them still have the same version of the array. And then an array copy is redundant in this memory copy because it's already available on the host and device. So we have formally denoted the availability analysis using the avail out notation, and here the A underscore host comma device means that the array A has the same version on host and device, and hence any memory copy is redundant. So in this example, we see that the array was available between host and device after the first memory copy, and it's still available after the use, and then finally it is redundant because it was available between host and device. So let's look at another example and see what happens when we replace the array use by array definition. So array definition would kill the availability of the array, and hence the array copy is no longer available after this definition. So if the array copy is no longer available, then this memory copy is no longer redundant. The details of our availability and anticipability analysis are in the paper, and we show how we use the availability and the anticipability analysis to do partial redundancy elimination of the memory copies. So we implemented our partial redundancy elimination implementation in the LLVM infrastructure, and we also implemented our intermediate presentation as an extension of the LLVM memory SSA. The client parses the OpenMP target offloading programs and lowers them to libopenmp runtime library calls. So we have to parse these library calls to detect the kernel regions in the code which are uploaded to the GPU, and also the memory copies introduced by the target offloading constructs used by the user. And then we use this information along with the LLVM memory SSA analysis, the alias analysis, and happens before analysis to finally construct our LLVM IR with the location aware SSA. And then we perform the algorithm lazy code motion, which removes the partial redundancy, and then finally we add all the optimized OpenMP memory map directives which copy the array only when required. For evaluation, we used 6 OpenMP FEC version 1.2 benchmarks and 4 other kernels, and these are the details of the hardware configurations we did our experiments on. So let's look at the runtime results. So the graph on the right shows the speed up in terms of runtime. The baseline here is the OpenMP default memory mapping. That is, we took the spec benchmarks, and then we removed all the explicit memory copyings specified by the programmer. So we made sure that the array is basically now being copied in and copied out whenever a kernel is being launched. That's the default behavior of the target offloading clauses. So every time a kernel is launched, the array will be copied in, and every time the kernel launch finishes, the array will be copied out. So that is our baseline from the benchmarks that we used. And then our LLVM implementation will optimize the memory copies and then insert the explicit OpenMP target directives for memory copy at optimal points. So the graph here shows that we were able to obtain significant speed ups in most of the benchmarks, and a geo-mean speed up of 2.3x was obtained due to our transformation. And some of the benchmarks like 504, we see almost a 10 times speed up because of our transformation. But in some other benchmarks like the 503 and 552, we see that our analysis failed to do any transformation, and the speed up was same as the baseline. We observed that pointer analysis or alias analysis failure was some of the reasons because of which our analysis also was not able to perform any transformation, and the stencil and the PEP benchmarks were some of the cases where we were not able to disambiguate the pointers and the arrays that they were referring to, and that's why our analysis failed. So that is one of the drawbacks of this analysis, that it relies on a strong pointer analysis to be able to do this optimization. To understand the reason for the speed up, in this chart we are showing how the memory copy time versus compute time decreased after our optimization. So in most of the kernels where we obtained a speed up, the memory copy time reduced significantly. As an example, if you look at the POLM-BM benchmark, the memory copy time reduced from more than 75% to almost less than 5%. As a summary, we formalized the problem of optimizing data movement across different computation devices. We developed an optimization framework which detects and eliminates the redundant data transfers, which was implemented in the LLVM infrastructure, and our LLVM implementation is able to achieve almost 2.3x geometric mean speedup on OpenMP 4.5 benchmarks. We will be soon open sourcing our implementation, and we are trying to improve the pointer analysis in our implementation to handle the cases which we were not able to handle in this paper. Thank you.
Yes, thanks to the authors for providing this interesting presentation. And again, I'm opening the time for questions. We have about 5 minutes before the planned break. So you are invited to go to the TO4 Architecture Compilers Slack and ask your questions there. Okay, we have the first question from Maciej Pawlik. It seems that benchmarks presented on graph were mostly bound by memory copy operations. Could you elaborate what is a limitation of typical scientific application, not a specific benchmark, or maybe what is the case with applications dealing with machine learning?
Yeah, am I audible clearly?
Sorry,
Hello,
I did.
am I audible? Okay, so yeah, so this is an interesting question. So the main reason that most of the applications are memory bound is that even for machine learning applications, so we need to for example do some computations on an input image. So the data needs to be copied from the host to the device. So in most of the applications, we observed that the memory copy was the limitation basically in the performance, but we didn't profile machine learning applications separately. That would be interesting to see what is the bottleneck for machine learning application. Then another reason is that, I mean, the compute performance of most modern hardwares keeps on increasing with newer generations, but the memory bandwidth is always a limitation, so that the memory bandwidth is not increasing as fast as the compute performance is increasing. So that is why in most of the applications, still the memory copy remains as a bottleneck. I'm not sure if that answered the question clearly. Okay, yeah, thank you.
Yes, it looks it does. So we have a second question from Tariq Ardukestani. Hi, thank you for the interesting talk. How was the mem copy operation carried through? Single core or multi-threaded?
Yeah, so the memory copies were carried out in single core. So basically, yeah, so the memory copy was also a blocking memory call. So the host issues the memory copy, and then a single threaded memory copy is performed, and then the host blocks on the memory copy to finish, and then the kernel is launched.
Does that answer your question?
Hi, thank you. So in many of the current applications, many applications are using multi-threaded mem copy because they want to utilize all of the available bandwidth. So that's why I asked my question, and thank you for your response.
Sure. Yeah. I mean, yeah, it would be interesting to see. Actually, we have observed that in many cases, even launching multi-threaded memory copy might not help because the bandwidth is anyway limited. So even if one thread is copying enough amount of data, that could be enough to saturate the memory bandwidth available. So it would be interesting to see in which cases one thread is not able to saturate the memory bandwidth, but multiple threads would be able to do that. Yeah, that's an interesting question.
Okay, so if there are no further questions, we are basically at the end of the session. Thank you all for attending. Thank you most of all the authors for providing the presentations and for all for the discussion. And I am closing the session now. And you are all invited to participate in not more than 10 minutes, basically, in the keynote. That is the next point in the program. Thank you.